Okay, can you hear me in the back? Are you going to be, can you mic up? Are you mic'd up?
I'm not.
Are you going to use the one on the stand or?
I can try it.
Yeah.
I'm going to be standing here anyways. So,
Okay. Good afternoon. I'm going to introduce Ian Cornejo, who's going to give his master's presentation today. Ian comes to us from the University of Illinois, I gotta get it right, Champaign-Urbana. Urbana-Champaign, crap. I thought I'd get it right. Urbana-Champaign, sorry, everybody there. And he had a double major in atmospheric science and environmental physics. And it was during a cloud physics class as an undergraduate that he got really excited about the microscale of hydrometeors and cloud modeling. So he joined my group not long after I got here in the beginning of summer 2020, and he was immediately supposed to go into the field to collect data for his project, and as we all know, nobody went anywhere in 2020. So Ian, we had to kind of scramble, and he came up with this really interesting project that he's going to present for you today. He did finally get to go into the field this summer. The project finally happened, so that's kind of the next steps. But I'll let Ian take it away.
thank you. Sound good? You good? Cool. So my talk is titled Orographic Controls on Extreme Precipitation associated with the Mei-yu Front. Before I begin, I want to acknowledge my funding through NSF, SIMS, as well as the Advanced Opportunity Fellowship. Before we can really start to begin to talk about Mei-yu Fronts, let's start really simple. What do we mean by extreme? A recent example that many of us may remember are the recent floods in Yellowstone this past summer. 100 millimeters of rainfall plus rapid snowpack melt resulted in damage to homes and infrastructure. Without a doubt, I would say this is an extreme event. Another impactful extreme rainfall event could be Typhoon Morkot in 2009. It also destroyed homes and infrastructure in Taiwan, but was the result of over 2,500 millimeters of rainfall. What links these two events together is the complex terrain that covered each environment. But as we add more and more of these events, we find that the designation of extreme becomes more and more contextual. Therefore, how do we begin to objectively study rainfall in extreme mountainous environments, given different locations and climates? Our approach is through partitioning rainfall into a few key ingredients. We start with Doswell et al.'s simple framework, whereby precipitation can be expressed as a rainfall intensity, R, and a rainfall duration, D. With these two variables, the scale of light to extreme rainfall emerges. Taking this a step further, rainfall intensity can be re-expressed as a precipitation efficiency, relative moisture density, and a vertical moisture flux. Similarly, rainfall duration can also be re-expressed as a storm relative length scale and an inverse motion scale. Rainfall intensity essentially increases with strong vertical forcing that we see in deep convective cores, and rainfall duration increases through strong horizontal forcing like we find in broad stratiform regions being fed moisture through something like a low-level jet. With this approach, individual rain events can be placed in an intensity duration spectrum and be compared with one another. Events like the Yellowstone floods and Typhoon Morkot highlight a need to incorporate topography into this framework. Thus, I'm trying to determine how terrain influences the ingredients that control the location, intensity, and duration of rainfall. The focus area for extreme rainfall and complex terrain is Taiwan, with the TAMEX field campaign in 1987, the combined SOMEX-TIMREX experiments in 2008, and the most recent being the joint Precip and TAHOPE experiments in 2022. With the predecessor campaigns and Precip in mind, we'll choose Taiwan to address our question. This is a population density map of Taiwan. The majority of the population lives on the western and northern coasts of the island, with the most densely populated region being Taipei Basin, with a population of 2.6 million. The reason for the gap further inland is illuminated by the topography. Two major mountain ranges, the Central Mountain Range and the Snow Mountain Range, cover roughly 2/3 of the island, with the highest peak being the Jade Mountain at just under 4 kilometers height. One of the more impactful mountains would be those found in Yangming National Park, which directly impact Taipei Basin. We'll find later on that when we discuss rainfall, the layout of the steep topography has a large role in determining the distribution of rainfall. This is a climatology of rainfall, averaged over Taiwan using various ground-based instruments over a 55-year period from Henny and colleagues. We'll focus on the bold green line, which is the 20-day running average. Rainfall peaks in the split summer season, the latter portion being the typhoon season, dominated by tropical cyclones, and the former being the Mei-yu season, dominated by Mei-yu Fronts. As the title of this talk suggests, we'll be talking about Mei-yu Fronts, with daily average rainfall peaking at 12.5 millimeters over the entirety of Taiwan, which exceeds that of the typhoon season. Translated from Mandarin, Mei-yu means plum rain, based on the seasonal fruiting of plums in China. It's also an East Asian phenomenon, so other names for it would be the Baiyu in Japan and the Changma in Korea. The Mei-yu signifies the transition from the weakening northeast monsoon to the strengthening southwest monsoon. On the right is the moisture transport prior to the southwest monsoon onset and after the southwest monsoon onset. The southwest monsoon is what's responsible for prolonging storms during the Mei-yu season through increased moisture transport from the equator. The boundary between the monsoons forms the Mei-yu Front, a quasi-stationary moisture front with a weak and shallow temperature gradient. On the right is a cross-section drawn using multi-Doppler instances and reanalysis. The post-frontal temperature anomaly typically reaches an average height of 3 kilometers, and the cross-boundary temperature gradient is 10 Kelvin or less. If we denote our front using the dashed line, typical prefrontal flow is moist monsoonal southwesterlies, and typical postfrontal flow is relatively drier northeasterlies. Prefrontal flow typically rises up and over the postfrontal flow, produce precipitation along and to the north of the wind shift line. What we're viewing here is Himawari 8 corrected true color during the day, and channel 10, or low-level water vapor brightness temperatures at night, from June 1st through 3rd, 2017. We're observing a broad Mei-yu front that spans from central China to the central Pacific. The ranges of brightness temperatures between -20 to -80 C along the Mei-yu front highlight numerous deep convective cells that propagate eastward along the stratiform cloud shield that act to intensify rainfall. This 3-day period and the Mei-yu front will be the focus of this talk. Although there was significant rainfall on June 1st, the heaviest rainfall was on the 2nd as the front made landfall near ZOZ and then progressed south through the island. Separate of the Mei-yu front, you can also spot near constant rainfall on the western slopes of the central mountain range. In terms of societal impact, there was widespread flooding, landslides, and damage to infrastructure, one of the most heavily damaged areas being Taipei Basin. For rainfall accumulation, we turn to the quantitative precipitation estimation and segregation using multiple sensors, or QP sums, which is produced by the Central Weather Bureau of Taiwan, which accumulates rain rates from 12 different radars, and then is corrected by over 1,000 rain gauges. The rampant flooding in Taipei Basin was the result of about 300 millimeters of rainfall in a 48-hour period. Two regions of more extreme rainfall are northern Taiwan, accumulating about 600 millimeters of rainfall in a 12-hour period along the northern coastline, stopping just short of the Yangming National Park, and central Taiwan, with the maximum rainfall accumulation found along the central mountain range of just under 1,500 millimeters of rainfall, or roughly 60 inches in a 48-hour window, much of which was due to the moist southwest monsoon precipitating on the windward slopes. For context, here's the cumulative precipitation for Madison this past water year, where we got about 35 inches of rainfall, or just under 2/3 the maximum of this event. Although Mei-yu fronts normally produce extreme rainfall, the rainfall produced by this event was enormously high. A potential reason why was proposed by Arcana and colleagues in 2019, whereby Tropical Cyclone Mora, which dissipated a few days prior in the Bay of Bengal, modified circulations in East Asia, strengthening both post and prefrontal flow with enhanced moisture transport, leading to enhanced moisture convergence along the front. For such an extreme event, we hope it was well forecasted, but unfortunately it wasn't. On the left is 24-hour QP-SUMS rainfall accumulation starting at 0Z on the 2nd of June. The right two panels are the forecasted rainfall accumulation for the same period using the WRF Ensemble Prediction System, or WEPS, as well as the ECMWF global model. Although the landfall was somewhat captured well, everything kind of breaks down as you go further south. The most notable feature, the Mei-yu rain band, is completely missing in both models, and the rainfall totals were severely under forecasted. QP-SUMS had a maximum accumulation of just over 1,000 millimeters in 24 hours, whereas WEPS and ECMWF only managed around 250 millimeters. Extreme events like these are difficult for most models to predict, and when you pair it with complex terrain of Taiwan, accurately capturing the mesoscale and microscale features becomes a challenge, even if you use a higher resolution model. This event qualifies as extreme in my eyes, and reworking our research question for this event, you can ask how orography modifies the precipitation caused by this event, whether it be through the location, intensity, or duration of rainfall. We can also ask how the Mei-yu Front itself was modified by topography, and we can also ask what tool is best suited to analyze topographic effects on Mei-yu Fronts in Taiwan during an extreme rainfall event. Regarding the last one, we've already seen that global models perform poorly in these circumstances, and that carries on into reanalysis. Our best bet would have been observations, but instruments like operational radars are limited in scan strategy, as well as extreme blocking in complex terrain. We also find that tools like radiosondes get launched too infrequently for an event that's so brief. Our solution was to use the WRF model, with all credit going to Yoonji Jang at Penn State, as well as Kristen Rasmussen and Jen DeHart at Colorado State. If you'd like, the list of some of our parameterizations can be found at the bottom left. An initial 40-member ensemble run was performed with 2 nested grids at 3 and 9 kilometer resolutions. Once a best performing member was picked based on observations, that member was downscaled using the N-down program to 1 kilometer resolution with 15-minute time steps. That run will be our control run. A second 1 kilometer downscaling was done, but this time with halved terrain to test orographic influence, and that run will be called half T. The choice to reduce the terrain was to make an environment like Taiwan with steep topography more like flatter parts of the world, where these results would become more generally applicable. In terms of performance, I think WRF did well. Rainfall distributions were fairly represented, with the maximum well capture along the central mountain range. Some initial differences that can be spotted are the positioning of the rain band off the western coast, changes in peak rainfall in northern Taiwan, and the rainfall on the lee side of the central mountain range. That being said, I believe the WRF model was able to capture key components that the global models were not able to. For example, global models do not even have a rain band extending off the western coast. This gives us some confidence to use this run to address our research questions related to topographic influences on Mei-yu rainfall. Now that we have a method of analyzing the case, we can return to the intensity and duration framework. To adapt it to our dataset, we use 2 proxies. For rainfall duration, we use a contiguous duration with allowance for 1-hour gaps in rainfall. For rainfall intensity, we use an average rain rate. Each grid point has a period of maximum rainfall, which will have a characteristic contiguous duration, as well as an average rain rate. These grid points can then be color-coded via the color matrix on the right to map out rainfall intensity and duration to create a bivariate color plot. The utility of this approach is being able to quickly see differences in intensity and duration between the control and half-T run. 2 regions stand out to me. First being a general decrease in duration in northern Taiwan with a decrease in terrain height. The second is in central Taiwan where we see a decrease in both intensity and duration. We'll look at both regions more thoroughly, starting with northern Taiwan. And just as a heads up, from here on out, all figures containing both model runs will have the control run on the left and the half-T run on the right. An orographic feature that might explain the decrease in duration in northern Taiwan is the Barrier Jet. This was extensively explored in the Taiwan Area Mesoscale Experiment in 1987, with its focus on northern Taiwan. It was found that these jets are common in the prefrontal sector of Mei-yu Fronts. The general understanding for the formation of this Barrier Jet is due to orographic blocking, diverting prefrontal southwesterly flow, which then converges with the mean flow downstream, thus creating a jet. We can understand the Barrier Jet more by understanding orographic blocking. When flow encounters a topographical obstacle, it can lift over that obstacle, and this would be called orographic lift. If the layer above the flow is too stable, however, the orographic lift can't overcome the stability, thus it becomes orographically blocked. When flow is orographically blocked, orographic lift is pushed upstream of the orography, and the flow deforms. A common method of finding orographic blocking would be the flow number, written out as the wind speed normal to an obstacle divided by the brunt by solid frequency, which is a measure of stability, as well as the obstacle height. If this flow number is greater than 1, the flow is unblocked. If the flow number is less than 1, flow is blocked. A secondary consequence of orographic blocking is a slowdown of flow found within the orographic deformation radius, which is defined as the brunt by solid frequency and the terrain height divided by the Coriolis parameter. Through idealized modeling of mountain ranges, Humbert and Wyman found that the flow number in tandem with the orographic deformation radius can be used to diagnose the scale and degree of slowdown induced by topography. If the flow number is less than 4/3, a deceleration is found within the orographic deformation radius. If the flow number is less than 2/3, stagnant zones with wind speeds near zero are also found within that deformation radius. In a scenario where the orographic deformation radius, L sub D, is far bigger than the length of your mountain range, L sub Y, then the deformation radius can only be as large as the mountain range length. In the opposite scenario, the orographic deformation radius is small relative to the terrain length. We can apply this to Taiwan using simple measurements from Lin and colleagues from 1991. We find that the orographic deformation radius, L sub D, is comparable to the length of the topography in Taiwan, L sub Y, for the control run, but relatively small in the half-T run. Therefore, the flow pattern of the control run is somewhere in between the extremes worked out by Humbert and Wyman, but the half-T run should exhibit a far shallower deformation radius. Assuming the barrier jet is formed through upstream orographic blocking, the differences in orographic deformation radius alone should result in different barrier jet strengths. These figures are a few hours past model initialization during the landfall in front and show wind speeds and wind bars at 900 millibar, which is a common height to find barrier jets in Taiwan. Both runs have a barrier jet, but it's approximately 10 knots stronger than the control run. This barrier jet seems to manifest from a slowdown of flow upstream of the jet in southern Taiwan. By eye, you could argue that slowdown only really starts at the coastline. But if we difference the wind speeds, it becomes more apparent that the slowdown expands far beyond the coastline. To determine if this slowdown is actually orographic in nature, we can take a cross-section through the highest peak in southern Taiwan, the Jade Mountain. Here we have the wind speeds along the cross-section with positive U-hat pointing toward the mountain. The dashed line is the coastline, and the black and white contours are the dry isotopes. Relative to the half-T run, there's a slowdown of flow in the control run, spanning the entire cross-section at low levels. Both model runs exhibit a slowdown of flow between the coastline and the terrain, with the control run also having near stagnant flow. Differencing the two model runs, the relative slowdown of the control run becomes more apparent. We find that tangential wind flow off the coast is faster above 2 kilometers for the control run, but faster for the half-T run beneath that level. Once you cross the coastline, this gradient goes with altitude. Since these are wind speeds tangential to the cross-section though, differences in wind speed can be attributed to flow into and out of the cross-section. Therefore, A method is needed to determine if orographic blocking could be the cause of the slowdown. My method was through manipulating the throw number such that the maximum terrain height h is always relative to the height of the measurement c. Here's what that looks like in practice. We now have a cross-section relative throw number based on the location of the measurement and the maximum terrain height, which in this case is the Jade Mountain. Red indicates orographic blocking. Therefore, the control run is blocked far beyond the extent of this figure, whereas the half-T run is only really blocked this really tiny sliver near the terrain. Thinking of blocking heights, we find that the control run is blocked between 2 to 2.5 kilometers, whereas half-T is blocked at most a half kilometer. This can somewhat explain why the tangential wind speed in the half-T run is faster than the control under 2 kilometers. Changes in wind speed above that level, however, can be attributed to wind direction shifts. It's no wonder that the barrier jet is stronger in the control run with substantially stronger orographic blocking upstream. That knowledge, how does this translate to rainfall? We're going to step through the landfall of the Mei-yu Front in northern Taiwan, reviewing 3 things in each panel. The first is wind bars at 900 millibar. The second is rainfall accumulation over the next hour. And lastly is a modified form of the Parfit et al. Frontal diagnostic F at 900 millibar. This is just a measure of vorticity and theta E gradient, which is then normalized by a climatological constant and latitude. Anything over 1 could be diagnosed as the Mei-yu Front, and the higher that value goes, the more confidence there is in that assessment. Many studies have adapted many ways of tracking the Mei-yu Front, but we found that this method works best when tracking the front on land in your topography. We begin at 20Z on the first. The front is making landfall in both model runs, with the frontal diagnostic aligning with the northern coastline. Heavy precipitation in the next hour is spatially correlated with the front. The barrier jet is found in the prefrontal sector, and it's approximately 5 to 10 knots stronger in the control run. 2 hours later, and the front is still anchored to the northern coastline of the control run. The half-T front, however, has already progressed south about 1/4 of a degree. Heavy rainfall still remains linked with the location of the front. Barrier jet in the control run has not diminished in strength, but the half-T jet has dropped between 10 to 15 knots in proximity to the front. Another 2 hours later, the control front has begun to move, but only really off the coast. On land, it still remains anchored to the northern coastline, while the half-T front maintains a linear orientation and presses further south. Despite discontinuity in the control front, rainfall on land remains as a linear band parallel to that of the off-coast front. The possible reason for why the control front is slow to progress south on land is due to the strength of the barrier jet. The barrier jet in the control run has remained over 50 knots within this 4-hour span. I see it as a rock in a hard place scenario, whereby the rock is the snow mountain range and the hard place is the Mei-yu Front. When push comes to shove, the barrier jet has to blow through one of those, and the front is more malleable than the mountain. Therefore, the front can't progress south. That's why we see southerlies and westerlies downstream of the jet on the northeastern coastline of Taiwan. We already know that rainfall is spatially linked to the front, so if you slow the propagation of the front to one region, that region will have to increase. That region will have to receive an increase in rainfall duration. That being said, there's a wealth of literature out there on fronts themselves being orographically blocked by terrain. To determine if the slowing of the front is caused by orographic blocking or by a strengthened barrier jet, we turn to orographic trajectory analysis. Parcels are released at 3 different locations, at 3 different heights, and at 13 different times, all being released prior to and during the landfall of the Mei-yu Front. In total, that comes out to 117 trajectories per model run. Shown here are the trajectories for just one location using the control run. We denote northern Taiwan as the gray area bound by the northern coastline in 24.75 north. And any trajectories that enter that box will be colored green, and any that do not will be colored red. If the barrier jet is key to slow down in front, then parcels from release location 3, which is the closest to the central mountain range, should enter northern Taiwan, since that's where upstream orographic deformation should originate from. Just isolating the first and third groups. we find that a significantly larger portion of parcels in the control run make it to northern Taiwan, while the half-T parcels overwhelmingly opt to summit the central mountain range. Counting up all parcels from all three release locations, we find that roughly half of the control trajectories enter northern Taiwan, while only 14% of the half-T trajectories make it. This gives us an indication that while orographic deformation of the front is plausible, a non-negligible contribution to the slowdown of the control front is due to a stronger barrier jet. Pulling it all together, we can say that orographic blocking in southern Taiwan leads to a strong barrier jet in the control run, which slows the southern propagation of the front. And if rainfall is spatially correlated with the location of the front, then halting the front in northern Taiwan acts to increase rainfall duration. So we've somewhat solved the decrease in rainfall duration in northern Taiwan for the half-T run. We can now turn our attention to central Taiwan, where the reduction in rain height led to decreases in both intensity and duration. This is a tricky area because there's no known prior work for the interactions of any kind of front whose orientation is perpendicular to a mountain range. We find that the placement of this front is important though. This is a climatology of 6-hour rainfall relative to Mei-yu Front placement, as shown by the gray boxes. Wang et al. Found that rainfall distribution is extremely sensitive to where the front is. It should be noted that Wang et al.'s determination, though, for frontal placement was set at the western coastline, that is because it is notoriously difficult to pinpoint the front on land near topography. I think one of the factors that leads to that difficulty is in determining what the post-frontal flow looks like. Prefrontal flow is, as one would expect, southwesterly. The post-frontal flow should be northeasterly, but we don't actually see that. And that's one of the big mysteries for maintaining the front over land in central Taiwan. What happens to the Mei-yu Front's post-frontal northeasterlies? This is a loop of 950 millibar theta E, wind barbs, and mean sea level pressure in the control run. We see a clear theta E gradient indicating the Mei-yu Front on the windward slopes of the central mountain range. However, we don't see post-frontal northeasterlies. So what's actually happening to them? We still have northeasterlies directly north of the front. In my eyes, there's two possibilities. What we see here is that post-frontal northeasterlies are ramping up with the lee side southwesterlies to form a cyclone on the lee side. This cyclone blocks any post-frontal northeasterlies from making it to the front. Another scenario would be that even if we have post-frontal northeasterlies and no cyclone, they become orographically blocked before even reaching the front. So how exactly is the front maintained near the terrain? We try to piece this apart by zooming in on the western slopes. We're now viewing 950 millibar wind direction, wind barbs, in the same Hartford et al. Frontal diagnostic from before, all for the control run. Starting in the prefrontal sector, winds are southwesterly, as one would expect. In the post-frontal sector, our northeasterlies first deform along the front, form westerlies, which is our cyan colors. These westerlies are then orographically deforming into northwesterlies and southwesterlies, the blues and the greens and yellows. The most important part are those northwesterlies because that's what converges with our prefrontal flow to maintain frontal continuity near terrain. In motion, we find that those post-frontal winds are important for pushing the front south, albeit slowly, because once the flow first deforms along the front and then again along the topography, the actual wind speeds are relatively slow when it converges with the prefrontal winds. In the half-T run, prefrontal flow is still southwesterly, as we expect. Post-frontal sector, however, is not really the same. Rather than deforming along the front and westerlies, post-frontal flow becomes northwesterly, completely skipping the orographic deformation step. These northwesterlies are stronger than those in control run and converge with the prefrontal flow to maintain the front. In motion, these strong post-frontal northwesterlies push the front farther south and faster than the control run. The effect this has on rainfall compounds on what we know in northern Taiwan. The heaviest rainfall is co-located with the positioning of the front, and on top of that, Orographic lift will also increase rainfall intensity near steep topography. Coupling these two together, and we find that front position near steep topography is very important for determining where the most intense rainfall sets up. This is irrespective of where the front is upstream of the topography, like we see in the control run. Depending on the pre- and post-frontal sectors, the front can progress south, slow, or fast. From what we've learned in northern Taiwan, slowing the fronts will increase rainfall duration. That being said, my hypothesis of the post-frontal sector is hypothetical based on simple wind direction plots. So zooming in, we have clear frontal detection at this time. We also have what I'm assuming is orographically deforming post-frontal winds. To nail down whether or not my hypothesis is correct, we can run another trajectory analysis. We use 7 release locations meridionally aligned in the post-frontal sector, indicated by the red dots, each with 5 different release heights between 400 to 800 meters ASL. To determine origin, you run a backwards trajectory, and to determine impact on lifting, you run a forward trajectory. We then stitch those two together to make one full trajectory. This is repeated at a comparable time and location for the half-T run. Therefore, each model run will have 35 total trajectories. The dashed line indicates where we stitch together the forward and backwards trajectories, and the different colors represent the different release heights. Starting with the forward trajectories, I would argue there aren't any significant changes to lifting potential in each run, with the exception of how rapid ascent is in the half-T run. Moving to the backwards trajectories, it should be noted that even though we release in the post-frontal sector, we can clearly spot parcels originating from the prefrontal sector, meaning at some point they cross over the front, though that isn't very surprising. In the parcels that originate in the post-frontal sector, however, take very different paths to make it to the release point. In the control run, they start off westerly and sharply turn clockwise into the release point. And this happens regardless of what height they're released at. In the half-T run, however, trajectories originate far off coast, slightly turning clockwise into the stitch point, possibly disputing if they actually deform along the front at all. Regardless, we see clockwise turning within each model run. Therefore, we should probably find a way of determining if that turning is due to orographic blocking. To do so, I've manipulated the flow number yet again into a Lagrangian form. For a given parcel, you can cut a cross-section along the wind direction such that the train height of views is always relative to that point in time and space. The utility of this approach is that if our parcel moves, you can just cut another cross-section with a new relative terrain profile. This can be applied to the entirety of the trajectory's path, assuming it is yet to summit the terrain. Here's what that looks like in practice. You find that for the most part, trajectories in the control run are orographically blocked prior to lifting over the central mountain range. On the flip side, the half-T run is the opposite, with most parcels unblocked. Both runs, the blocking or lack thereof happens regardless of if the trajectories originate in the pre- or post-frontal sector. Therefore, the sharp turning we see in the control run is likely attributed to orographic blocking as hypothesized. So pulling it all together, how is a front maintained near a mountain range in the control run? It's not necessarily a step, but the post-frontal winds are first deflected off the lee side cyclone. Second, post-frontal winds deform along the front into westerlies. The third step is for these westerlies to orographically deform into weak southwesterlies and northwesterlies. These northwesterlies can converge with the prefrontal flow to maintain the Mei-yu Front, which rainfall is co-located with on the windward slopes. For the half-T run, both steps are similar, except those post-frontal winds off the coast curve into strong northwesterlies that not only converge with the prefrontal flow, but actively push the front south. Same as before, convection forms along the wind shift line. All that being said, the half-T run is still a bit of a mystery to us, because we also have parcels originating far off coast with little turning. We don't necessarily understand why post-frontal winds don't turn into westerlies like we see in the control run. That being said, it's still something we're still actively exploring. So lastly, just wrapping up with some conclusions. Extreme rainfall is a ubiquitous phenomenon across the world. It produces high socioeconomic impact, remains a forecasting challenge. Both the damage and the forecasting challenge are heightened when extreme rainfall meets complex terrain. Through modeling and modifying the terrain of the June 2017 Mei-yu Front case, a reduction in terrain height led to decreases in rainfall duration in northern Taiwan and decreases in rainfall duration and intensity in central Taiwan. We found that reducing terrain height weakens the barrier jet, which resists southern propagation of the front less than in control. The longer the front is in northern Taiwan, the greater the rainfall duration. In central Taiwan, a proposed mechanism for frontal maintenance near a mountain range is through convergence of post-frontal orographically deformed winds with prefrontal southwesterlies. This mechanism helps push the front south, but not as fast as the half-T run. Like northern Taiwan, slowing the propagation of the front leads to increases in rainfall duration in the control run. And we also find that stronger orographic lift also leads to more intense rainfall in central Taiwan. Looking forward, I hope to carry on this work and shift gears, looking at data captured during the Precip field campaign. This campaign ran from May 25th to August 10th this year in Taiwan to capture both the Mei-yu season and the typhoon season. Precip's goals are similar to my own, using the same intensity and duration framework, but expanding beyond Mei-yu fronts to include diurnal convection as well as tropical cyclones. I'll be on a similar path as my master's research, but looking toward orographic influences on cloud physics associated with Mei-yu fronts. While this forefront performed well in replicating the mesoscale, it didn't necessarily perform well in replicating the microscale. To get around this, my PhD will heavily rely on data captured by the S-pole radar during the Precip field campaign. The strengths of the S-pole radar with the operational radars in Taiwan is its ability for greater vertical coverage, high resolution, and user flexibility in scan strategies. A large advantage of S-pole radar is its dual pole capability, which will also be helpful in observing the rain microphysics. Regarding Precip, we've got great Mei-yu front cases, especially IOP1, which was a 2-day Mei-yu front event at the start of the campaign. That would act as a good comparison to the 2017 case. And then to contrast those two, we'll also look at IOP3, which was a 6.5-day IOP, also a Mei-yu front, which will most definitely fill out the duration side of our intensity and duration framework. Before I start taking questions, I'll just quickly acknowledge all the people who got me here, I guess. I first want to thank Angela for taking me on as a student and proving to be one of the most patient people in the world when it comes to advising me. Really appreciate you guiding me through this whole process. I also want to thank my committee, John Martin and Tristan. I'm really thankful for all the help that you've given me so far, and I look forward to working more with you guys. Big thank you to all the members of Precip, Hope, and T-Part 2, those two are companion projects. Most specifically, the Orographic group, the Radar QC group, as well as the modeling group. I want to thank the Row Lab, Ben, Anthony, Giselle. I don't want to leave out Andrew and Clayton at UW. The High Impact Weather Group that meets semi-regularly. I want to thank all of you. You guys have seen my research blossom from nothing to what it is right now, so that's really great to see. We also have a small CWB precipitation group that meets also semi-regularly. Great to have conversations with people who have parallel research projects as our own. And then broadly, I just want to thank the AOS faculty, staff, and grad students. You know, I don't know where I would be without any of you, whether it be through my research or just keeping me sane through the research process. And that goes similarly for my family and friends. And then I just want to wrap up with acknowledging my funding again with NSF, SIMS, and AOF. And with that, thank you, and I'll take any questions.
Questions? Steph?
When you're manipulating the drawing number, is what it's called, right? I wanted to ask
I think with a reasonable degree, yes, because the Front number is more of a theoretical tool that most of the literature I've seen it used in is for idealized mountain ranges, and when it is applied in a actual case, it's used very generally, whereas how I'm applying it, it's actually very specific to different levels, as well as to parcels and trajectories. I think as long as you view it within that context, I think it makes sense, and I think the results are still relevant. But I guess that's just an asterisk you should put on it when you use it, the way I use it. Yeah.
You started your presentation by talking about the forecast models couldn't capture the precip, and you showed how important orography is. Do you know how correct the topography within the forecast models are? If they get the topography right but not the precip, or do the forecast models not get the topography right and that's why they can't capture?
Yeah, I would probably say so. I think the finer the resolution, the more accurately these models will probably be able to capture, probably the most important being the mesoscale phenomenon. If you look back at the models themselves, they actually completely miss the Mei-yu rain band going further south. And I think if you actually watch the progression of those models through time, instead of the snapshots that I give, you'll find that the front actually just stops in northern Taiwan, which that doesn't necessarily explain why the rainfall totals are so low, but I think the distribution is relatively reliant on where those models push the front further south. So if it stops if it stops in northern Taiwan, you're not going to get the extreme rainfall you see in central Taiwan. Yeah.
Do you think the treatments you see between the two cases you're looking at, the control and half T, could be used to predict if you were to do like double T or a quarter T? Would you expect to see those trends continue?
I guess I'll respond with maybe quarter T, you might see similar results, but doubling the terrain, I think you start to break the physical meaning of what you're looking at, because if Taiwan's maximum terrain height is 4 kilometers, give or take like 100 meters or so. If you double that to 8 kilometers and you're relatively close to the coastline, that becomes really unphysical, and you're essentially just building a wall in the middle of the Pacific. I mean, potentially the results might double, but I can't necessarily say if. I can't think of many papers that look at such a steep orographic boundary.
Maybe I should restate that question. How confident are you that the model runs have captured reality, given that you've got 2 model runs only?
Well, I guess just based on the performance of the control and the control and observations in terms of rainfall, I'd say it does pretty well. I've looked at these pretty extensively, breaking it down minute by minute and whatnot, and it does kind of not capture it pretty well. The timing is off in a lot of these situations, but I think in the grand scheme, as long as it gets rainfall accumulation right, it's outperforming global models, it outperforms reanalysis. That's the best we can take, I guess. And then if we had really good observations, that would be the next best thing to kind of analyze these sort of cases. But I'm pretty happy with how it went so far, and I'll accept how good or bad it does.
Yeah, just on the more technical side of things, how familiar are you with the way that QPE sums works? And I guess my specific question is, you'd mentioned beam blocking and other issues around topography. I guess I'm wondering how accurate the rainfall estimates are in what you're showing here. You're using that as kind of a benchmark, and whether or not you think there's any issues, especially when you get into these extreme terrain areas.
Yeah. I don't know if I have those figures in here, but I trust it a lot more on land than I would say over the ocean, because these are rain gauge corrected, so there's no rain gauges over the ocean, so I would say I put quite a bit of faith in them. They have a pretty dense network within the terrain as well, so it's pretty accurately measured, and I believe they're constantly adding more and more rain gauges, so it's gotten better and better. I could talk to you more about this later on. There's constant improvements to this product, and I've met with one of the creators of it while in Taiwan, and they seem to put a lot of faith into how it performs in complex terrain.
I guess maybe just a quick question, so are they using different elevation scans and like sort of combining the reflect, like I guess I'm just wondering how they're actually doing the surface precipitation at like
Yeah.
3 kilometer altitude over the mountains?
How I understand it is that each radar has a weighted rain rate. They kind of mosaic that out into a 2D grid, which will serve as the baseline assumption of what the rainfall accumulation is. And then they choose the surrounding rain gauges near that to correct it. I don't know if there's any details on how much of a correction there is via the rain gauges. From the papers I've read, I never saw anything of that sort, so I don't know actually how much the rain gauges are correcting them by. Yeah, I should probably look into that. Yeah.
You've shown the importance of wind facing topography and having them with a pretty significant result in the precipitation. But could you comment on how the B-side topography may play into that?
Yeah, as you can probably tell, I kind of skipped over anything that happens with the lee side. Partially, it's because the model doesn't actually well represent what happens in observations. But also, I don't foresee it being a huge contributor to rainfall on the windward side, which is what our focus is on. That being said, I've looked at model reflectivity from the warp runs, compared it to mosaics of this event, and the rain band should extend across to the lee side. It does that in observations, but it doesn't do that in the warp control run. So it's obviously getting something wrong. In terms of how that affects everything, I think the biggest factor would be what happens with the lee side cyclone in northern Taiwan. If I remember correctly, in the observations, there's a lee side front that actually pushes further south. So the situation of what happens here is different. Again, I don't actually know how much that impacts the windward side. Yeah, maybe I should focus a little more on what happened on the lee side. So,
I mean, it's the best populated.
yeah, I mean, there's no one, yeah, but it's an important dynamic, and there's actually quite a big gap in what happens with this lee side front and how important it is for what happens on the windward side, because there is some correlation there, I guess. Yeah, I'll look into that.
I was wondering if you knew how common this rain band on the windward side is. Like, is this something that's really unique to this event, or is this something that happens frequently during the monsoon season?
It's pretty common. I guess what I'd say more is it's the determination of how far south the front actually goes. Sometimes it can clear the entire island, go to the southern half before regressing further north. But for the most part, you'll see the rain band extending off the western coast, just due to MCSs forming far off coast and then propagating eastward with the mean flow. Because even though I say pre and post frontal flow, once you go above maybe 2 kilometers, it's all pretty much westerly, so everything just slams into Taiwan.
I think it would be interesting to see how often that band is in a particular place, because to me, when you did your parcel movements, like all those parcels, they look like they went through like a gap in the mountain range that kind of lines up where this rain band is. And so I'm wondering if that gap is setting where this rain band sits, and if it likes to be there more
Yeah, that's actually a really good point. We've kind of labeled like this region as like the concave region. And
Yeah.
there is some climatology on that being actually a pretty common spot for extreme rainfall to set up.
Yeah.
As to whether that's due to the Mei-yu rain band, I don't know off the top of my head. But yeah, this area in particular is actually pretty interesting in the mechanics of the layout of the terrain. And it has a definite influence on how the rainfall is distributed in central Taiwan at least.
Yeah, I think it'd be really interesting to see like whether or not that rain band like has a distribution of what latitudes has specific latitudes that likes to be at this.
Yeah, I agree. Ruja, you'll go next. Yeah.
Great talk, by the way. This is really, really interesting. I'm wondering if you could please, if you thought about it, just touch base a bit on the specific microphysical characteristics that you're interested in studying for PhD and just kind of the linking variables you might be looking at.
Yeah, I think broadly, I'm pretty interested in changes to the warm rain processes that happen inside and outside the Mei-yu Front, and whether or not those get modified further if we go into steep topography and outside of that steep topography. So I've already done a little bit of precursor work on this using observations based on this case. As I said prior, the operational radars in Taiwan aren't very great, so the results were limited. But I have been doing a little bit of microphysical inferencing using S-band radar data that's operational in Taiwan, mostly in the context of warm rain processes between the 0 to 10 kilometer range, mostly to do with how this impacts the intensity and duration of rainfall.
Just to follow on that, Juliet, just about not great. Taiwan's operational radars are quite similar to NextRad, but they're not all upgraded to dual pol. So a complicating factor of using operational data for this is the one radar that's on the west coast near where the rain band is located wasn't dual pol at this time. So using preset data, all the radars we deployed are all dual pol, so that gives you a lot more information on microphysics, but we just couldn't do that for this case because not all operational radars are. So I just wanted to make that clarification point because that's one limitation so far. Yeah.
Ruja?
Yeah, I'm just curious that how important is the orientation of your front with respect to the topography? Like, if what happens if the direction is a little bit changed, do you still see the similar results or not? And whether a loss speed change causing a deflection to that would cause anything to that?
That's a tricky question to answer just because the orientation of the front, for the most part, when it's in central Taiwan, is pretty linear and meridianal or zonally aligned. There is a case that we have from 2020. It was in southern Taiwan, and it was oriented more southwest, northeast, that kind of orientation. It's very rare that it goes beyond that, like, little bit of inclination, I guess. In terms of how this impacts rainfall, I haven't really looked into that much. I haven't done a lot of climatology work. So in the context of this 2017 event, it's hard to say because it doesn't change in orientation a whole lot. Just looking at two different events, it also doesn't really make a huge impact. It's really treated much like I see it as like a hose. It doesn't really matter what orientation that front is, wherever your nozzle is, it's just going to release all the water. So, yeah. Thanks. Anything else?
Right, thanks.
Okay, thank you.
Yep.